4 days after magnitude 7.3 to 7. 4 earthquake tore into the Middle America Trench off the coast of Chiapas. The aftershocks out there are not fading the way they were supposed to by now. They are still arriving in clusters. Multiple days after the main shock, moderate earthquakes were still being logged near Tapachula, and the strongest of the later aftershocks has been estimated in the magnitude 6 to 6. 5 range, arriving well after the sequence, should have quieted into background noise by the textbook decay curve. By the end of this, you will understand the one measurement that would settle what is actually happening down there and why, 4 days in, nobody fully has it yet. The stretch of seafloor off the coast of Chiapas, southern Mexico, has not gone quiet since Friday. On July 17th, a major earthquake ruptured the Middle America Trench near the Mexico-Guatemala border. The United States Geological Survey placed it at magnitude 7. 3. Mexico's National Seismological Service placed it at 7. 4. The epicenter sat roughly 48 kilometers southwest of the town of Aquiles-Cerdan, near the port of Puerto Madero, at a shallow depth of around 10 to 15 kilometers, depending on which agency's model you read. Shallow ruptures like this shake a wide area hard, and this one did. Millions of people across southern Mexico, Guatemala, and El Salvador felt moderate to strong shaking. The Pacific Tsunami Warning Center issued a threat message within minutes. Small waves of roughly 1/3 of a meter showed up on tide gauges near the coast, and the warning was stood down within hours. Once it was clear nothing larger was coming ashore. No deaths were reported. A handful of injuries occurred in Chiapas, along with cracked walls, some collapsed ceiling panels, and scattered gas leaks. Buildings in Villahermosa, Tabasco, were evacuated as a precaution. Mexico City felt it, but authorities determined there was no threat to the capital and did not activate the seismic alert system there. For the first hour or so, the sequence behaved exactly the way the science says it should. Foreshock activity had actually preceded the main event, including a magnitude 4, 7 roughly 90 minutes earlier, though nobody recognized it as a foreshock until after the fact, which is itself an important detail we will come back to. Then, within about an hour of the main shock, a cluster of significant aftershocks arrived in rapid succession, several in the magnitude 5 range, and one that reached magnitude 6.0. A magnitude 6.0 aftershock is almost precisely what the statistics predict as the largest aftershock following a magnitude 7. 3 to 7.4 main shock. That is not an alarming number. That is the textbook answer. By the end of that first day, the people tracking this were describing the sequence as entirely ordinary, a productive but expected aftershock pattern on a subduction interface that everyone already knew was capable of large earthquakes. Then the weekend happened, and the fade did not fully come the way it was supposed to. Instead of a clean, monotonic decline toward background seismicity, the region kept producing moderate earthquakes in bursts, clusters separated by quieter stretches rather than one smooth taper. Multiple magnitude 4 and 5 events continued to strike the same general offshore zone through Saturday and into Sunday, with additional aftershocks still being logged near Tapachula as the weekend wore on. Some reporting on the sequence has placed the largest of the following aftershocks in the magnitude 6 to 6. 5 range, which, if accurate, sits right at the edge of what would normally be expected and is worth taking seriously without overstating it. That is the actual story here, not a prediction, not an alarm bell. A sequence that was called ordinary by day 1, and then kept behaving in a way that made seasoned observers want to keep watching closely rather than file it away. It is worth pausing on what these magnitude numbers actually represent, because the scale is not intuitive. The magnitude scale is logarithmic. Each whole step up represents roughly 32 times more energy released. A magnitude 6. 5 releases something on the order of 1,000 times more energy than a magnitude 4. 5. And the main shock that started all of this released hundreds of times more energy than any single aftershock in the sequence so far. None of the individual aftershocks recorded since Friday have been damaging on their own, sitting offshore, where the shaking on land is a firm jolt and little else. What makes a sequence like this worth paying attention to is not the size of any one event. It's the number of them, the timing, and whether the rate is decaying the way statistics say it should. Here is why the offshore location of this sequence matters so much for how confidently anyone can describe it. A subduction zone is not one fault. It is at least 2 entirely different earthquake-generating structures stacked on top of each other at the same spot on the map. Off the coast of Chiapas, the Cocos Plate is sliding beneath the North American Plate at a rate of roughly 6 to 7 centimeters a year. As it descends, it produces 2 separate populations of earthquakes. The first lives on the interface, the contact surface where the descending slab is locked against the plate above it. These are the megathrust earthquakes, the ones capable of reaching magnitude 8 and magnitude 9, the ones capable of generating large, destructive tsunamis. The second population lives inside the descending slab itself, below the interface, where the plate bends and pulls apart under its own weight as it sinks. These intraslab earthquakes can also be large, but they are a physically different process running on a different set of faults entirely. Whether this weekend's aftershock burst was happening on the shallow interface or deeper inside the bending slab is not a minor technical detail. It is close to the whole question. A sequence clustered in the shallow range, roughly 10 to 15 kilometers down, is plausibly sitting on the interface itself, the geometry in which foreshock sequences to a larger megathrust rupture can occur. A sequence sitting deeper, closer to 30 kilometers or more, is more likely happening inside the slab, a different and generally less concerning process. Different agencies monitoring this sequence have, at various points, produced depth estimates for the same individual earthquakes that disagree by a factor of 2 or 3. That is not unusual for offshore earthquakes specifically, and it is worth understanding why, because the explanation is genuinely mundane rather than suspicious. Earthquake depth is measured largely by timing the difference between seismic waves that travel directly to a monitoring station and waves that bounce off the Earth's surface first before arriving slightly later. That measurement works well when instruments are distributed all the way around an epicenter. It degrades sharply when every available station sits on one side of it, which is exactly the situation for an earthquake happening dozens of kilometers out in the Pacific off a coastline. All the stations are on shore in one direction, and the geometry is lopsided, so depth solutions get loose. On top of that, when an automated system cannot converge cleanly on an answer, many catalogs default to a fixed placeholder depth rather than reporting genuine uncertainty. Different monitoring agencies also run different velocity models, different assumptions about how fast seismic waves travel through the specific rock beneath that specific stretch of coast, and draw on different sets of stations entirely. Feed the same raw waveforms into 2 different models and you can get 2 different depth answers, and neither agency is hiding anything by publishing both. A depth disagreement of this size on an offshore event is routine, not remarkable. It is a measurement limitation, and it is exactly why, 4 days in, the interface versus slab question for this sequence does not yet have a clean answer. As more of the automated solutions get manually reviewed by seismologists working through the actual waveforms in the coming days, some of those depths will shift, in some cases substantially, and the picture should sharpen. Underneath all of this sits an uncomfortable fact that no amount of instrumentation has ever fully solved, and it's the reason honest coverage of a sequence like this has to stay careful rather than dramatic. Foreshocks are only identifiable in retrospect. Something like 5 to 10% of moderate earthquakes are followed within days by something larger, which retroactively reclassifies the earlier event as a foreshock. At the same time, a meaningful share of large subduction earthquakes genuinely are preceded by foreshock activity. Both of those statements are true simultaneously, and together they leave working seismologists in a position where there is no reliable real-time signature that tells you which category a given swarm belongs to. The overwhelming majority of earthquake sequences that look like this one are not the prelude to something larger. There simply isn't a clean instrument reading that lets anyone promise that in advance. The clearest illustration of exactly this problem is also the most sobering one on record. The magnitude, 9. Zero Tohoku earthquake that devastated Japan in 2011 was preceded 2 days earlier by a magnitude 7, 3 earthquake in almost the same location. At the time, nobody called that foreshock a foreshock. It was treated, correctly given the information available in the moment, as a significant earthquake with its own ordinary aftershock sequence. That is exactly how this Chiapas sequence has been treated over the past 4 days, and it is exactly how it should be treated. Because in the overwhelming majority of comparable cases, that treatment turns out to be correct. This is not a prediction about Mexico specifically. It is simply an honest statement of what the science can and cannot promise. Anyone telling you with confidence which category this sequence falls into is telling you something the instruments genuinely cannot support right now. There is, however, one genuinely useful and checkable thing to hold on to here, because it gives this story a testable spine instead of just a feeling. Seismologists watching subduction sequences like this one generally treat a specific pattern as the threshold that changes the picture if multiple magnitude 6. 0 or larger events begin appearing in a sequence, one after another. That shift in the pattern is treated as raising the odds of something larger still to come, rather than the sequence simply being a normal stress release process working itself out. As of the most recent reporting on this sequence, that threshold has not clearly been crossed. A single magnitude 6. 0 arrived within roughly an hour of the main shock, right where statistics say the largest aftershock should land for an earthquake this size. Reports over the following days describe additional aftershocks reaching into the magnitude 6 to 6. 5 range near Tapachula, which is worth watching closely without treating it as confirmation of anything larger building underneath. 1 or 2 aftershocks landing in that range is still broadly consistent with a large, productive, but ordinary sequence. A repeated pattern of multiple magnitude 6+ events stacking on top of each other is the specific signal that would change the read. The reason this particular threshold carries real weight on this particular stretch of coast is that the region has already demonstrated what it is capable of, and recently. In September of 2017, a magnitude 8. 2 earthquakes struck the Tehuantepec region on almost the same stretch of subduction zone, the largest earthquake to hit Mexico in a century, killing nearly 100 people. That earthquake is instructive in 2 directions at once. It proves this segment of the Cocos North American boundary is capable of producing something far larger than what just happened. It was also mechanically distinct from Friday's earthquake, an intraslab normal faulting event roughly 47 kilometers down, the slab tearing itself apart under its own weight, rather than a shallow thrust rupture on the locked interface. This coastline has recorded multiple magnitude 7+ earthquakes within roughly 150 miles of this same stretch over the past several decades. It is not a quiet piece of the planet, and it never has been. Zoom out even further and the pattern holds. The Middle America Trench runs for well over 1,000 kilometers along the Pacific coast of Mexico and Central America, and essentially the entire length of it has produced large, damaging earthquakes at one point or another over the past century, from Michoacan and Guerrero in the west to the Chiapas-Guatemala border in the east. Seismologists studying this trench have long discussed the idea of seismic gaps, stretches of a subduction zone that have gone unusually long without rupturing compared to their neighbors, on the theory that strain is quietly accumulating there rather than being released in smaller, more frequent events. Identifying a gap is straightforward using historical earthquake catalogs. Predicting when or whether it will actually rupture is a different problem entirely and remains one of the genuinely unsolved questions in seismology. Nothing about the current Chiapas sequence changes that broader picture one way or the other. The trench was capable of large earthquakes before Friday, and it remains exactly as capable now. It helps to understand the statistical rule that seismologists actually use to describe aftershock decay, because it explains why should have quieted down by now is a more precise claim than it sounds. Aftershock sequences generally follow what is known as Omori's law, an empirical pattern observed for well over a century across earthquake sequences worldwide, where the rate of aftershocks falls off roughly in proportion to the inverse of elapsed time since the main shock. In plain terms, you expect a lot of aftershocks in the first day, meaningfully fewer by the 3rd or 4th day, and a small fraction of that original rate by the 2nd week. It is a statistical law, not a guarantee for any individual sequence, and it describes an average smooth decline, not a straight line. Real sequences bounce around that average curve constantly, with quiet stretches followed by bursts, and a single active period 4 days out is not automatically evidence that the underlying decay has failed. What matters is whether the overall envelope of activity averaged over the noise is still tracking the expected curve, or whether it has genuinely departed from it. 4 days into this sequence, the honest answer is that the rate has stayed elevated for longer than the simplest version of that curve would suggest, without yet crossing into territory that changes the underlying diagnosis. It's also worth being specific about what a tsunami warning does and does not represent, since the sequence of alert and stand down on Friday is sometimes read, incorrectly, as evidence of a system that either overreacted or was withholding information. The standard practice for any shallow, offshore earthquake above roughly magnitude 7 is to issue an initial threat message within minutes, based purely on the earthquake's location, depth, and magnitude, before there is time to know how the seafloor actually moved. That initial message is deliberately precautionary. As tide gauges and deep ocean pressure sensors report back actual wave heights in the following hour, the warning is either escalated or, as happened here, stood down. Once measured wave heights confirm there is no significant hazard. A small tsunami, on the order of 1/3 of a meter, did register on coastal tide gauges near Puerto Madero, confirming the earthquake displaced the seafloor roughly as expected for its size, but at a scale far below anything destructive. That sequence, alert, measurement, stand down, is the system functioning exactly as designed, not a false alarm and not a cover-up. That is the honest current state of things, 4 days in. The sequence has run hotter and longer than the simplest textbook decay curve would predict. The depth picture is genuinely ambiguous. Between agencies, and the one specific line that would meaningfully change the assessment, a repeated pattern of magnitude 6+ aftershocks has not clearly been crossed. And while attention has stayed fixed on that offshore zone, moderate earthquakes have also continued to show up elsewhere across the wider Central American and Caribbean seismic corridor over the same stretch of days, which raises an obvious question worth answering. Carefully, rather than waving away, is this Mexican rupture somehow pressurizing the neighboring plate boundaries? The physics on that question is worth walking through directly, because part of the intuition holds up and part of it does not. When a fault slips, it genuinely changes the stress on nearby faults. Regions where stress increases as a result get pushed measurably closer to failure. This is called static stress transfer, and it is well-established science. It It is also strongly limited by distance, meaningful within roughly 1 to 2 rupture lengths and falling away rapidly beyond that. For an earthquake in the magnitude 7, 3 to 7.4 range, with a rupture patch on the order of 50 to 80 kilometers, that effect realistically reaches out to perhaps 100 or 200 kilometers. Anything on a separate plate boundary 1,000 kilometers away or more is well outside the range where static stress transfer can meaningfully explain a coincidence in timing. There is a second mechanism that genuinely does operate at longer range: dynamic triggering, the transient stress carried by the seismic waves themselves as they sweep past a distant fault. It is real and well documented. The 1992 Landers earthquake in California triggered seismicity across the western United States at distances of hundreds to over 1,000 kilometers. But dynamic triggering is a weak effect. It acts almost exclusively on faults that were already sitting right at the edge of failure regardless of what happened off Chiapas. So the honest reading of any moderate earthquakes appearing elsewhere in the region over these same 4 days is layered. Anything happening a few hundred kilometers away, further along the same general subduction system toward to Central America, is a plausible, if weak, candidate for a genuine, if modest, relationship. Anything happening on an entirely separate plate boundary 1,000 or more kilometers away, in a region that produces earthquakes on its own every week, regardless of what happens off Mexico, is far more likely to simply be coincidence. That said, the instinct to keep an eye on the wider region east of Chiapas is sound on its own independent merits, earthquake activity there or not. The plate boundary running east from Guatemala through the Motagua and Polochic fault systems, out into the Cayman Trough and along the Swan Islands transform, is a genuine active left lateral strike slip system moving on the order of 20 millimeters a year. In 1976, that system produced a magnitude 7, 5 on earthquake on the Motagua fault that killed an estimated 23,000 people, one of the deadliest earthquakes in the hemisphere's modern history. The Chiapas sequence sits very near the western end of that same broader boundary, close to the complex junction where the Cocos, North American, and Caribbean plates all meet. That is a reason to keep monitoring that stretch of coastline generally. It is not, on its own, evidence that anything happening there right now is connected to Friday's earthquake. Which brings up the question most people actually want answered when a sequence like this makes headlines. Does an earthquake this size off southern Mexico raise the risk of a major earthquake somewhere much further away, like California? The answer is a clear no, for the same reason laid out above. Static stress transfer is effectively zero at a range of 2,500 kilometers or more, and dynamic triggering from a magnitude 7, 3 to 7, 4 earthquake at that distance is far too weak to meaningfully move anything that was not already sitting on the exact edge of failure. Nothing that happened off Chiapas this past week changed the underlying probability of a major earthquake in California. That is not meant as reassurance. It is simply physics, and it cuts both ways. What remains true, entirely independent of anything happening in Mexico, is that certain sections of California's own fault systems, including portions of the southern San Andreas and San Jacinto systems, have been measured by researchers as sitting at some of their highest accumulated stress levels in roughly 1,000 years. The southern San Andreas has not produced a major rupture since the Fort Tejon earthquake of 1857, an event estimated around magnitude 7.9. That is close to 170 years of accumulated strain on a fault system that geologically does not stay quiet forever. None of that changed last week. None of it will change because of what happened off Chiapas. The earthquake in Mexico did not cause any of it, and it did not make any of it more or less likely. What an event like this does is prompt a much larger number of people to go looking at seismic hazard maps they otherwise ignore, which is a reasonable and healthy reaction as long as the two separate stories don't get blurred into one. That distinction is worth protecting carefully, because the loudest claims that tend to circulate after a sequence like this one depends on blurring exactly that line. The idea that agencies somehow know something bigger is coming and are quietly sitting on it. There is no validated short-term earthquake prediction method possessed by any monitoring agency on Earth. Full stop. Aftershock forecasts for sequences like this one are published openly as continuously updated probability tables, not hidden internal assessments. Every seismic catalog referenced in coverage like this is a public feed that anyone can pull and check for themselves. Any lingering tsunami-related database entries tied to Friday's original alert reflect the automated warning system doing exactly what it's built to do, issuing an initial threat message. And then standing it down once, measurements confirmed the danger had passed, not evidence of anything being suppressed. So where does this actually stand today, 4 days out, and what specifically would change the picture from here? 3 things are worth tracking over the coming days, and all 3 are publicly checkable by anyone willing to look. The first is that magnitude 6 threshold. It has already been named explicitly by people watching this sequence, and as of today, it has not been repeatedly crossed. If multiple magnitude 6 zero or larger events start stacking on top of each other in the days ahead, the assessment shifts from a large but ordinary aftershock sequence toward something warranting genuinely elevated concern. Right now, that has not happened. The second is the batch of revised, human-reviewed depth solutions still working their way through the catalogs. When those publish over the coming days, this sequence resolves toward one of three pictures: activity concentrated on the shallow interface, activity concentrated deeper inside the descending slab, or a genuinely more complicated picture involving more than one structure at once. Each of those three answers means something meaningfully different, and right now that specific question remains open. The third is whether moderate earthquake activity continues to show up along the broader plate boundary running east toward the Cayman Trough and the Motagua system. If it does, in a sustained way rather than as an isolated event, the case for some genuine, if modest, connection gains real weight. If it does not continue, anything observed so far was almost certainly coincidence in a part of the world that produces earthquakes on its own every single week, with or without help from Chiapas. The honest bottom line, 4 days into this, is that the most likely explanation for everything described here is that a genuinely productive subduction interface produced a large but fundamentally ordinary aftershock sequence, that the decay of a real sequence is statistical rather than perfectly smooth, and that bursts separated by quieter stretches are the norm for this kind of process rather than the exception. That reading is very probably correct. It is also true that this particular sequence ran hotter and longer than the simplest textbook curve predicted, that later aftershocks reaching into the magnitude 6 to 6.5 range are worth taking seriously without overstating them, and that the depth question underneath all of it remains genuinely unresolved on a trench that produced a magnitude 8.2 earthquake within living memory in 2017, and is unquestionably capable of producing something that large again someday. Both of those readings are on the table right now. The instruments and the seismologists working through this week's waveforms are going to publish clearer answers over the next several days, and that, rather than speculation, is the thing actually worth watching. If you live along that stretch of coast, or anywhere in an active seismic zone, the standard unglamorous preparedness steps are the ones that actually matter, regardless of how any of these open questions get resolved. Know how you'll get updates from your local civil protection or emergency management authority. Know your evacuation route if you're near the coast and a tsunami alert is ever issued again. Secure heavy furniture and anything that could fall in continued shaking, and keep a basic emergency kit accessible. None of that depends on knowing whether this sequence is happening on the interface or inside the slab. It's the same good practice either way, and it's worth having in place before the next update, whatever it turns out to say.